This is problem 6-20 on page 278. Determine the force in each member of the truss and state if the members are in tension or compression. The load has a mass of 40 kilograms. Now, in this problem set, we're supposed to use the method of joints. So let's do it. First of all, let's make a sketch of the truss that we're given. Pin joint and rolling joint. And then point A is here. There's supposed to be support. I haven't drawn it very well. Let's see, this moves up, comes back, and there's some internal support structure. Like this. So point G is here, point B is here, point F, E, and C. There is a tensile load this way at point D. Now, one detail about this is that there's actually a load I'm not showing here, as well as a pulley. I guess I should go ahead and draw it that way to make it clear so you can understand what's going on. So let's put a pulley here. And there's a load, it's 40 kilograms, but in order to calculate its weight, we have to multiply by 9.81 meters per second squared. So the tension in the rope then is 392.4 newtons. Now this rope is attached to the wall, so there's also a tension of the same amount going back to the wall. We don't care about forces on the wall, what we care about are forces on the truss. So we can simply leave it this way. Now, I didn't copy down all of the geometric dimensions. I'll let you look at the picture for that. But the pulley has a diameter of a radius of 0.1 meters. So, if we sum moments about point G, taking counterclockwise as positive, you know what, I may need some of that geometry. It's not many dimensions, so let's just put them on. So we've got what? 2.5 meters here, all the way up. Let's see, to the center of that point, which is D, 3.5 meters. And across this way, all the way to D, we've got 6 meters. Otherwise, you won't know what dimensions I'm referencing. So anyway, there's our geometry, and I went ahead and calculated the length of GD. Let me put that length on the free body diagram because it'll fit better. I guess I should make a free body diagram before I try to sum moments, shouldn't I? Something like that. We've got a reaction AX at point A. Forgot to mention that was point A. GX, and also, of course, GY. And tension, out here, I'll try to offset it a bit from from point D because they are offset by 0.1 meters. But I went ahead and calculated the length of this side, and I got about 6.946222 meters. I don't know why I wrote down so many decimal places, but there it is. Anyway, so now summing moments about point G, taking counterclockwise as positive, we got to be careful here. Point G, you'd think it would be a moment arm of 3.5 meters for the tension, but remember there's a pulley radius here, 0.1 meters, so it's actually 3.6 meters multiplied by T. So this tension causes a positive moment about G, but then this tension causes a negative moment. So minus, now again, you'd think it would be 6, but it's actually 6.1 to get all the way out to that tension location. And other than that, there's also AX that will have a moment about G. So plus AX, and its moment arm is in fact only the 2.5 meters that we're given. So 2.5 fit a little better. 2.5 meters equals 0. Now, of course, we know the tension, so what this equation will do is yield AX, and AX then is 6.1 T less 3.6 T divided by 2.5. These are meters, 3.6, 6.1, 2.5. You can see where they come from. They're all meters. They just cancel. Well, 6.1 less 3.6 is in fact equal to 2.5, so this comes out simply to T. In other words, AX, the reaction, equals the force T. So that's kind of interesting that the tension and AX are exactly equal to one another. So this must be 392, you know what, let's put it over here. I'm going to leave the free body diagram on this one, 392.4 newtons. And I'll keep the label AX so I don't forget what it is. Okay, well, what does that mean? Well, if we sum forces in the horizontal direction, what that means then is GX must be 0, because look, AX is taking all of the load T at A. So GX is not even there, it's not needed, right? It's unnecessary. So GX, if we were to sum forces, we'd have the tension in one direction, AX in the other direction, and GX would be left out to dry, right? There'd be nothing for it to do, so GX would be 0. If we sum forces in the Y direction, notice that the only thing that can offset this tension acting down is GY up, and so GY must also be equal to the tension, or 392.4 newtons. Okay, so that's what sum of forces in the Y direction tells us, is that GY equals the tension. So pretty straightforward free body diagram. All right, so now that we've got all of the reactions, we're supposed to calculate the load in all the members. All right, so let's look at point A to start. Point A will have, I'll assume, tensile loads, AG and AB. And of course, there is the reaction at the wall, AX. If we sum forces in the horizontal direction, we have AX plus ABX, the horizontal component of AB. And that's it. That should sum to 0. So what does that mean? Well, that means AB, let's just do it this way. AX equals negative AB, and then that horizontal component would be how much? Well, if you look at the geometry, what you'll realize is that this is a 45-degree angle. And so what that means is that the relationship between the hypotenuse of any force on this triangle and the vertical and horizontal components will be a 1 over root 2 relationship. Okay, so if I want just a horizontal component, I need to multiply by 1 over root 2. Or in other words, divide AB by the square root of 2. But notice I already know AX, it's AB I'd like to know. So AB must be, well, let's see, negative root 2 AX. So if you take the square root of 2 and multiply it by AX, which is 392.4, you will find the force in member AB. And what I'm going to do is put the force numbers into my original diagram. So of course we're plugging in here, negative root 2, 392.4 pounds. That comes out to negative 555.94 newtons. And note that this must be compression, because I assumed tension. I got the opposite, I got a negative, and therefore it is compression. Okay, fine. Now what about if we sum forces in the vertical direction? Let's go back to black so it shows up nicely. Summing forces in the vertical direction, the Y direction, we have AG plus AB in the Y direction equals 0. That's it. There's nothing else. Rearranging this just a bit, AG then is equal to the negative of ABY, which would be equal to negative AB over root 2. Not surprisingly, AG comes out to be the same magnitude as AX because these two forces add into AB, and AB is at a 45-degree angle. So AG comes out to, well, let's put it over here on the diagram. Remember, AB is a negative thing, so if you plug in negative 555.94 over root 2, we get back what we kind of started with early on. We get back the force in AG of 392.4 newtons. And since it's positive, this is a tensile load. Guess I could be consistent. All the forces will be in newtons. So I'll just put C or T after it to indicate compression or tension. So 392.4 is the tensile load in AG. Okay. Well, that's all the information we can glean from point A. What about if we move on? Well, maybe to point G. All right. So we already know that there's a tensile load AG equal to 392.4. We'll assume AB is a tensile load, assume GF is a tensile load, and then we've got the external load GY equal to 392.4 newtons. Now hopefully immediately you begin to see, oh, we don't really have a problem. This is actually a very simple problem because we already know AG is 392.4. GY, the force from the pin onto this point, is 392.4. So these two, summing forces in the vertical direction, what will we have? GFY plus 392.4 from the external reaction minus AG. But AG is 392.4. So what does that tell you? Well, that tells you the Y component of GF is 0. Therefore, GF itself must be 0 because the force at this point on GF has to lie along GF. It has to have some horizontal and vertical component, but the vertical component is 0, therefore the horizontal component is 0 as well. So what we just discovered is that there's no force in GF. It is a 0 force member. What else? Well, if that's the case, if there's no force in GF, then there would be nothing to offset the force from AB because look, there's no external load in the horizontal direction. So AB is also 0. Summing forces in the horizontal direction is a trivial equation. It simply says AB equals 0. So we can write that this is 0 as well. Okay, so that takes care of GB and GF. Let's move on then. How about if we move to point B and see what happens? All right, so here's point B. There could be force in member FB, force in member GB, although of course we already know there's none there, GB is 0. Force in AB and force in BC. But that's it. Those are the four members that are connected together at point B. As I said, we already know that GB is 0. And so if we were to sum forces in the horizontal direction, we get negative ABX. Now I know AB is compressive. So if I were to actually plug in numbers here, I'd plug in the negative, or I'd plug in this number, this negative number, and let the signs work themselves out. Plus BCX. Notice there's no horizontal component of FB. So this tells me that the horizontal component of AB equals the horizontal component of BC. Well, now wait a second. AB and BC act along the exact same line, so their geometry force triangle relationship would be exactly the same, which means AB equals BC. These two are exactly equal to each other. And so what that means is that if these two are equal to each other, let's make the picture clearer, there's no way that FB can have any load in it, because if it does, it would have a component in this direction, And that component would tend to throw this point off, right? There's nothing to balance out this point in that direction. Or another way to say this is, since these two are equal, the projection of FB, the horizontal component of FB, must be 0. Okay. All right. Well, that means that FB is 0. We're finding a lot of zero force members here, which is actually kind of nice. FB is 0. And we know that AB and BC are equal. Now notice I assume that AB and BC were both tensile. But they're exactly equal to each other, meaning that I assumed wrong, and BC is in fact in compression and has the same magnitude as AB. Well, why don't we take care of one more point, point F, and see what happens there. You might already see what's going to happen. Well, point F would have, let's see, FB, FC, FE, and GF, but wait a second. GF is 0 and FB are 0. So if you think about what that means, it's easier to see if we do this. What that means is there's no way for what is this, FC? There's no way for FC's horizontal, well, that's all it's got. There's no way for its horizontal nature to cancel any of the vertical component that FE has. So FE has to be 0, and therefore FC is 0. So we're getting a whole lot of zeros here. This is actually a pretty easy problem once you realize what's going on. FE is 0 and FC is 0. Notice that F is a lot like E and B is a lot like C. We've got the same thing going into these points that we had going into F and going into B. And we'll get the same result, namely that EC is 0 and ED is 0, and the force in CD is negative 555.94 and is a compressive load. Basically, the way this geometry is set up is that all of the load from this pulley, from these two tensions, just travels right down here. And the only purpose of GA is to pull up, since A is a roller. Now, in the real world, there would actually be some force here because we couldn't perfectly balance the load that way. Right? There would be a little bit of error in the direction of the tensions or error in manufacturing of the truss, but it'd be close enough. We don't really have to concern ourselves with it. There is a check we can perform. Basically, what I just claimed is that the pulley only has force that it applies to the truss. Let me draw just a bit of the truss here. I've separated out point D, one for the truss, one for the pulley. There are only loads acting down this line. In other words, if I think about the pulley free body diagram, we'd have to have the load T as I've drawn here, right? These are the external loads from the rope. This is the support from the truss. And so equal and opposite forces acting on the truss on point D mean that we should add these two tensions, and sure enough, since they are the same magnitude, we would get a vector acting right down the line CDBA. And so that check proves that what we've done so far makes sense. Now, if the angle of this truss member A to D is a little bit different, then of course the other members will be required in order to maintain static equilibrium.